By now, you've almost certainly used some generative AI tool to write text, learn about new topics, generate images and videos, or even write code. And guess what? Generative AI is also becoming increasingly popular in engineering and design. Today, we can generate CAD models from text prompts and even make decisions about materials and manufacturing within design workflows, and potentially much more. But then, recent studies also show us that people can become over-reliant on these tools, offloading their thinking and weakening critical reasoning, even in fields like engineering and design. In this work, we wanted to flip this narrative. We asked, what if instead of directly giving me solutions, an AI agent could talk to me and help me reason through my own decisions in a design problem? To explore this idea, we built an AI-assisted tool using structural design as our specific example. Imagine that I need to create a structure that can withstand a given load, while also using as little material as possible. These kinds of trade-offs are quite common in engineering design problems. Let's see how the tool can assist with this problem. In the top right, you can see my performance metrics. On the left is a chat window where I can talk to the AI agent. The structure is fixed at the top and bottom left corners, and there's a 100 kg load applied to the middle of the right edge. I'll start by trying to reduce the amount of material in the structure, since that is the objective that's challenging in this case. I can do this interactively by moving nodes, adding new nodes, filling regions, or deleting elements entirely. For example, if I remove this truss element, I'm close to reaching my material objective. But now, the structure's deformation increases significantly. I'm not entirely sure why that happened, so I've asked the agent. Notice how it doesn't just give me a solution. It explains what's happening to help me reason about the change, and then suggests multiple different directions to explore. Based on that, let me try adding central connections between the load and the supports to distribute forces more efficiently. And you can see that the overall performance improves, and I'm moving closer to meeting both of the objectives. Now, this was an interaction that was initiated by me, but like any good collaborator, the agent within a tool also takes initiative during the process, where it asks reflective questions based on the changes that I've made to help me think more carefully about my design decisions and the reasoning behind them. So, how does the agent have such context-aware conversations? It is essentially powered by a structured framework that is built on large language and vision language models. At its core are 5 contextual channels of information: the problem context, the state of the current solution, including visuals and underlying representations, the history of iterations and dialogue, evaluation signals like stress plots, and a target reference structure. Together, these channels create a high level of contextual fidelity. But what happens when that context is reduced? To find out, we built 2 different agents, a high-fidelity agent with full context and a low-fidelity agent with limited context. Our goal was to understand how contextual fidelity shapes how we think, talk, and act during a design activity. To study this, we ran a between-subjects experiment with 46 participants across 3 groups: a non-AI control group, a low-fidelity group, and a high-fidelity group. Their task was to design a cantilever beam and an L bracket to meet the material and deformation objectives. Looking at the results, access to the agents did not significantly change task success rates, but it did change how people designed. The high-fidelity group produced solutions closer to the target references, even without ever seeing them, suggesting that the agent subtly guided better design decisions. Looking at process data, such as the design space exploration patterns, also showed some clear differences. The control group relied on a trial and error based method of exploration, while AI-supported groups explored more strategically and made deliberate, reasoned changes. Conversation patterns also differed across groups. High-fidelity users sought more targeted help, used the AI more strategically, and felt more confident in their agents, likely due to its more specific feedback. The low-fidelity users, on the other hand, invested more mental effort in building their own understanding through broader discussions. The control group, however, reported the most frustration. Okay, so after all this analysis, which agent is better? From a broader perspective, we see that the problem-solving experience is influenced differently by different levels of contextual fidelity. For example, the high-fidelity agent promotes help-seeking behavior, while the low-fidelity agent encourages deeper thinking. And in reality, we often need both of these capabilities when solving complex problems. In design, for instance, the early stages benefit from more conceptual conversations, while later detail-oriented stages benefit from more specific discussions. So rather than choosing one approach over the other, what we really need is an adaptivity in the agent, one where it can shift between these modes to better support designers. Such adaptability could positively influence design quality, strategies, conversational dynamics, and even the overall learning experience. As generative AI becomes embedded in complex domains, we don't have to default to systems that think for us. This work takes a step towards showing that by designing AI as a reflective partner, we can augment human reasoning rather than replace it. Thank you so much for watching.